All right, let's dive right into this explainer. We're going to completely demystify one of humanity's absolute greatest engineering achievements, the rocket engine. We're looking right past all that smoke and fire to really understand the incredible physics making it all possible.
Picture it, a breathtaking launch at sunrise. The countdown hits 0, engines ignite, massive flames, thick smoke, and that glorious slow-motion liftoff. You are watching a machine producing enough raw power to literally rip itself away from Earth's gravity.
Now, from the outside, it looks like absolute magic. But how does a rocket engine actually work? To truly get it, we have to zoom inside the vehicle and look at the physics. Because, how exactly do we harness that much energy without blowing the entire thing apart?
So here's our flight plan. First, we'll look inside the rocket. Then follow the fuel flow. Break down the chemistry of combustion. Figure out how it creates upward thrust. And finally, follow it as it leaves the Earth.
All right, Chapter 1, Inside the Rocket. Let's peel back the metal for a transparent cutaway view. Now, unlike a jet engine that breathes air from the atmosphere, a rocket has to carry its own air, specifically an oxidizer, stored in massive propellant tanks right alongside the fuel. These enormous tanks feed down into high-pressure pumps, drop directly into the combustion chamber, and then blast out through that iconic exhaust nozzle.
Moving right along to Chapter 2, the fuel flow. To build up the crazy amount of pressure we need, we have to move those massive amounts of liquid into the engine incredibly fast. Step 1, the propellants leave their tanks. Step 2, they get pushed by pumps that build immense pressure. We're talking on the order of 100 atmospheres here. And Step 3, they slam into the injectors. These injectors are explicitly designed to spray and collide the propellants together inside the combustion chamber, shattering them into tiny, easily burnable droplets.
But before we even ignite that mixture, consider this number. 3,300, as in 3,300 degrees Celsius inside that chamber. That is over 6,000 degrees Fahrenheit. That is literally well beyond the melting point of the copper alloys the chamber is built from. So to keep the engine from completely melting itself, it requires some seriously advanced cooling techniques, like actually running the freezing cold liquid propellant through the walls of the chamber first.
Which brings us to Chapter 3, Chemistry of Combustion.
This is where things get truly violent. Igniting these chemicals triggers a massive exothermic reaction. In a fraction of a second, it converts all that stored chemical energy into rapidly expanding hot gases. This causes the internal pressure and energy inside that tiny reinforced chamber to just absolutely skyrocket.
Now, there's a big difference in how we actually burn things. Solid fuel rockets are relatively simple. The propellant is a pre-mixed solid grain, and the casing itself just acts as the chamber. Once you light it, it burns until it's completely empty. But liquid propellant rockets, they keep the fuel and oxidizer completely separate. And that gives us the incredible superpower to control, stop, and even throttle the thrust mid-flight. And the result of that intense combustion, just look at this staggering number, 4,500. Those superheated expanding gases exit the rocket at 4,500 meters per second. To put that into perspective, that is roughly 15 times the speed of sound at sea level.
So, Chapter 4, Creating Upward Thrust. How exactly do those super fast gases actually lift millions of pounds of solid metal off the launch pad? Well, it all comes down to Isaac Newton's third law of motion. Because the engine pushes that high-speed gas violently downwards, the exact same amount of force pushes the engine upwards.
To really visualize this, think of a balloon. If you just had a hole, like a deflating balloon with a tapering opening, the combination of air pressure and friction means the balloon is actually being pulled by the air, not pushed. But a rocket engine uses a convergent-divergent nozzle. This specific shape allows the expanding exhaust to press hard against the walls as it expands outwards, and that roughly doubles the total pushing force.
This is the brilliantly designed de Laval nozzle. The hot gases are squeezed and literally choke at the narrowest part, the throat, hitting exactly Mach 1, the speed of sound. Then, the moment they enter that iconic wide bell shape, they dramatically expand and accelerate to massive supersonic speeds. It is an amazing thermodynamic trick. It's converting random, chaotic thermal heat energy into purely kinetic, upward thrust.
And this specific engineering creates an unparalleled power-to-weight ratio. Check out this incredible stat. 180.1. That is the thrust-to-weight ratio of SpaceX's Merlin 1D engine, meaning that engine can literally lift 180 times its own weight. It's just wild.
Finally, let's look at Chapter 5, Leaving the Earth.
Right at T0, the rocket needs absolute maximum thrust just to fight gravity. Then, as it ascends into the sky, it's battling intense atmospheric drag, which, by the way, is exactly why they have those tall, thin, highly aerodynamic nose cones. Eventually, it drops off its empty stages to become lighter and lighter, pushing completely through to the blackness of space to hit orbital or escape velocity.
Now, once you're in the vacuum of space, there's no air to push against, right? And obviously no air to breathe. But remember, because a rocket carries both its fuel and its own oxidizer, it operates perfectly. Actually, it operates way more efficiently in a total vacuum. It proves that total momentum is perfectly conserved in a closed system. The faster the mass of the exhaust shoots one way, the faster the massive rocket flies the other way. Looking back at Earth from orbit, taking in that cinematic view of satellites and the moon, you can truly appreciate what it took to get there. Rocket engines are, without a doubt, among the greatest engineering achievements in all of human history. They require us to completely master extreme thermodynamics, fluid dynamics, and Newtonian physics just to unlock the universe for humanity. So the next time you watch a launch, ask yourself, what other seemingly impossible boundaries are we going to break once we truly understand the physics behind them? Thanks for joining me on this explainer. I'll catch you in the next one.